So starting exponential functions and graphs, we're going to look at lesson 21.1, exploring exponential patterns. We're going to identify data that grows exponentially and compare the rates of change of linear and exponential data. All right, so looking at the paragraph there, we have Raymond Hall, a graphic artist, needs to make several different size draft copies of an original design. His original graphic design sketch is contained within a rectangle with a width of 4 centimeters and a length of 6 centimeters. Using the office copy machine, he magnifies the original 4x6 design to 120% of the original design size and calls this his first draft. Raymond's second draft results from magnifying the first draft to 120% of its new size. Each new draft is 120% of the previous draft. Complete the table with the dimensions of Raymond's first 5 draft versions showing all decimal places. So we're going to take 4 and we want to multiply it by 120%. So when we increase it by 120%, we need to convert percentage to a decimal. So what's 120% as a decimal? 1.2. So we're going to, each time we're going to increase the dimensions. We're going to magnify them by 1.2. So we're going to multiply. So we're going to take 4 times 1.2. Okay.
5.76, 6.912 times 8.29.
Oh, I lost
and 11.
Oh, okay. That's good to know. So it was 11 point something? Okay. We'll just, you may need that. Alright, so now for this next one, our length, because it's the width and the length are being multiplied by 120. So this one is Alright, so questions on how we got those numbers?
Yeah.
Multiplied by 1.2.
Oh, why?
Why? Because it says that he magnified each draft by 120%. So we have a scale factor of 1.2. And so if you increase the width, since he's just putting it on the photocopier, it's saying increase by 120%. Have you guys ever done that, like on a photocopy machine, where you've increased something and it goes by percent?
We're not allowed to use it because you go for notes or else that's sort of higher.
Well, you can do it, if you go to the, photo center and increase the picture size. You can kind of Well, someday you guys will make copies and you'll be at work and you'll be like, okay, I need to, increase the size of something. So it tells you to increase the percentage, but it does the length and the width. It does everything proportionally. And so last year in geometry, you learned about scale factor. And so when you apply a scale factor, when you're keeping things proportional, you're increasing all of the dimensions. And so we increased the width, but we multiplied that by 1.2, and we did that to the length as well. All right, so now looking at number 2, we have the resulting draft for each magnification has a unique width and length There is a functional relationship between the number of magnifications n and the resulting width w. There is also a functional relationship between the number of magnifications n and the resulting length L. What are the reasonable domain and range for these functions? Explain. So domain is what we're putting into it. So what's going into our original function? Like what are we starting with?
4 and 6.
4 and 6. So if we are increasing them
By 120%.
by 120%, what's a reasonable starting point? What's the reasonable minimum value for our length?
0. 4. 6.
6. So our length,
20.
we're starting at 6. Are we ever going to be smaller than 6?
No.
No. Are we ever going to, can we always increase it by 120%? Or whatever we have, we can increase it, right?
Yep.
So what would be a logical starting spot for our length?
4.
Right, for our length, 6. So our L value is always going to be greater than what? Greater than 6.
How many centimeters in an inch?
2.56. Alright, so for our width, what's the minimum that our width is ever going to be if we're just increasing by 120%? 4. So our width is always going to be greater than or equal to 4. Alright, so if we look at the number of magnifications, what's the minimum times that we can magnify our, the minimum times that we can magnify? We can do 0, right? And we just have our original. So our x value is going to be anything greater than or equal to 0. Alright, so our domain is the number of magnifications we're doing. And so that's going to occur a minimum of 0 times, because we either magnify it or we don't. And then our length and width, our length is going to be anything greater than or equal to 6 centimeters, and our width is going to be anything greater than or equal to 4 centimeters. Alright, so plot the ordered pairs n of w from from item 1. Use a different color or symbol to plot the ordered pairs of n of L. And yeah. Alright, so alright, so what would be our first? So if I'm going to do black, and that's going to be our width. So at 0 magnifications, what's our width? 4.
It was a dream. Oh yeah. He woke up, but he didn't kept moving on. There's a bunch of snow globes.
Alright, so at 1 magnification, what is our?
And then 7.2.
And then 3 magnification. What was 2?
5.76.
Oh, 6.912.
What?
And then what was 3?
3 is 6.912.
Okay, so 2 is 5.7.
Two crickets in there. You're messing us up.
Alright, and then 3 is?
And then 8.1 like that new thing.
What?
That you screw off.
It was 8.1.
Like all the younger class.
What was 8? What it was 8 point what?
8.2.
And then 5.
9.953.
Are you exactly precise on that?
Precise.
Get organized.
Alright, so then what is our L? What was our 0 magnification? That was 6, right? Yep. And then 1 magnification?
7.2.
Alright, let's mess this one up too.
And then 2,
14.92992.
8.64.
3,
10.368.
4,
8.54.
12.416.
and then 5.
14.929942.
Your website.
Alright, then 5 was 14 something.
14.929.
Alright. So our graphs look like that, more or less, right?
They look almost the same.
In and out.
They both look like they went up about 120%.
They do look like they're both increasing.
How do you know that?
20%.
What the hell?
Alright, so use the data in item 1 to complete the table. So from 0 to 1, so we're going to subtract them. So we're going to do it both for the width and the length. So let's take 30 seconds to fill that in real quick.
About 35 seconds.
I like it.
Alright, we can do 30.
Oh, you had to say. No.
Was not good.
Alright, so we have our table filled in. So from the graphs in item 3 and the data in table in item 5, do these functions appear to be linear? So are they linear?
No.
So what's linear mean?
It means
They go along with each other.
So is it are they straight lines?
No.
No. So remember, if it's linear, and here is the slope-intercept form. If it's linear, it's increasing at the same amount by our slope, right?
Grow a little bit.
So are these graphs, do they have a constant slope?
No.
No.
No, ma'am.
No. As we're getting bigger, we're increasing more, correct? These numbers are getting bigger as we go down our the table. All right, so express regularity and repeated reasoning. So explain why the table below contains that can be represented by a linear function, or an equation to show the linear relationship between x and y. So here, what are we doing each time? So from 8 to 5, what's happening?
-3.
All right, and then from -3 to -1. So from -1 to +1. From 5.
Same thing.
All right, so since the x and the y are increasing at a constant rate, is this linear?
Yes.
Yes. So how do we find the slope of
It's 2 -2/3 or no?
other way?
Oh.
So remember, slope is rise over run. It's your y's, your change in y over the change in x.
So it's
So
-3/2.
-3/2. That's our slope. So now we need our y-intercept. So our y-intercept is when our x-coordinate is 0. So in between here. So since we don't have that, we can use the point slope form to get our equation. So pick a point on that line. So we need an x
1
and
and
1.
2. 1 and 2.
So y minus, was that +2? So y minus 2 equals our slope of -3/2 times x minus 1. So we can leave it like that, or we can distribute. Since we are algebra 2, we're going to go ahead and simplify. So what is 3/2 plus 2? What's 2 as a fraction? 2/1. So I need it to be a fraction over 2. So what number divided by 2 is 2?
2.
So 4/2. So this is +7/2. So there's our fraction. those are equations. So this equation represents this. So if we plug in any of those x and y coordinates, plug the x in for x, we should get the y as our output.
I wish I can remember this. I don't.
Did you just realize that?
Yeah.
All right, so let's look at B. So what are we increasing each time? So to get from 3 to 7, what are we doing?
What do you mean? You're better than this?
So from 2 to 5, what are we doing? From 7 to,
Double.
and then from 5 to 11, what are we
And I
doing?
got one wrong. I thought you were talking about the whole. Yeah, that's it.
That's it again. This is 6.
The last one. That's it. That's fine.
All right, so even though these numbers are different, what do we notice about 3 over 4, 6 over 8, 6 over 8, 9 over 12? They all reduce to the same thing, right? 3/4. So what is our slope for these?
4
Other way. Y over x. So 4 over 3. So then we can do the same thing. So with this, we're increasing or decreasing at the same rate. So these represent linear functions, right? So when we plot these points, we're going to get a straight line.
Attention please, the state has issued a tornado watch drill for this area.
Oh,
Stay where you are and please listen
I need to go get my dog.
for further instructions.
So.
you don't buy a house.
I hope so can live.
All right. So number 7, we want to consider the data in the table below. You guys know where we're supposed to go, right?
In the
Outside.
We're going to go outside and then to that center hallway, like where the bathrooms are at. No, it's a drill. It's a drill.
I want to suck tornado.
I've never seen it. I've never.
Neither have I. I want to go right.
Yeah, I want to.
All right.
I was in that middle of conversation. I realized what water said.
All right, so number 7. So we want to consider the data in the table below. So we have 0 to 1. We have a change of 1.
Where do we go for today?
Isn't that big?
I just, yeah.
Said it.
We go grab vacuums and start sucking air.
I bet you probably just.
Go to the nearest and last window.
Or we can just hide under a desk.
I'm sorry.
Target's
Like
movement.
yeah.
The target's movement. If you just stay still,
Without run.
you're just solid. It's like a T-Rex. So
So in letter A, can the data in the table be represented by a linear function?
Yes.
So let's see. So do we have a constant slope? So from here to here, we have +1, +1, +1, +1, right? So our x's is constant. Right here we have minus 12.
divide by 2, divide by 2.
Never mind. All right, so it's not linear, but
Close enough.
very good observation. We are dividing by 2 each time. So each one of these is decreasing.
Honestly, I just kind of plus 2.
It was right. Sometimes that's okay. So describe any patterns that you see in why they're dividing by 2 each time. Alrighty. So we want to consider the data in the table from item 1. How does this relationship of data compare to the data in the table of item 7? So with this one, we're dividing, so it's no longer, is this going to create a linear equation? Are we going to have a straight line? No. All right. So that is it for that.